This little expression terrifies more engineering students than any other. E to the j omega t. A number, raised to an imaginary power. What could that possibly mean? You can't multiply a number by itself an imaginary number of times. And yet this expression is the foundation of Fourier, Laplace, filters, communications, all of it. Here's the secret the textbooks bury: it is not a power at all. It is a rotation. Once you see that, the entire subject of signals and systems unlocks. No black boxes. Let's build it from scratch. Meet the complex plane. Real numbers live on the horizontal axis. Imaginary numbers live on the vertical axis. Start with the number 1. An arrow of length 1, pointing along the real axis. Now multiply by j. The arrow doesn't stretch. It turns 90 degrees, counterclockwise. Multiplying by j is a 90-degree rotation. Multiply by j again, rotate another 90 degrees, and you land on -1. And there it is. J squared equals -1 is not a weird algebraic rule. It is just 2 quarter turns making a half turn. Every mystery in this subject traces back to this one picture. Keep it in mind. If multiplying by j is a quarter turn, what is a rotation by any angle theta? Draw the unit circle. A point on the unit circle at angle theta has a horizontal shadow of cosine theta, and a vertical shadow of sine theta. So one point on the circle is both waves at once. Euler's formula simply names that point, e to the j theta equals cosine theta plus j sine theta. The exponential is the position. Cosine and sine are its shadows. Why the letter e? Because its derivative is itself times j. Its velocity is always its position rotated 90 degrees, and the only motion whose velocity is always perpendicular to its position is a circle. That's the whole proof, in one sentence. Watch the arrow sweep. This is the machine that generates every sinusoid in engineering. Now replace the fixed angle theta with omega t, an angle that grows with time. E to the j omega t is an arrow spinning at omega radians per second. As the arrow spins, watch its horizontal shadow. Plotted against time, the shadow draws a cosine. A sinusoid is not a wiggle, it is a rotation, viewed edge-on. And here is the identity we'll use for the rest of the series. A real cosine is the sum of two arrows spinning in opposite directions, their vertical parts cancel, their horizontal parts add. That opposite spinner is the famous negative frequency. Nothing spooky. Just clockwise. One last question. Of all possible signals, why do we insist on building everything out of exponentials? Feed e to the j omega t into any linear time invariance system. Out comes the same exponential, merely scaled by a complex number h of j omega. Same frequency. Same shape. The system cannot change what the signal is, only how big and how shifted. Mathematicians call this an eigenfunction. Engineers call it the reason the whole subject works. Decompose any input into exponentials, scale each one by h, add them back up, and you've solved the system without touching a differential equation. That decomposition has a name, the Fourier transform. That's where this series is headed. Let's make it concrete, gate style. Evaluate e to the j pi over 3. Step 1, apply Euler. Cosine of 60 degrees plus j sine of 60 degrees. Step 2, evaluate. 1/2 plus j root 3 over 2. Step 3, and this is the habit to build, read it geometrically. Magnitude 1, angle 60 degrees. A point on the unit circle, 1/3 of the way to vertical. You never needed to raise e to an imaginary power. You just turned. Everything else in signals and systems, convolution, Fourier, Laplace, sampling, the Z-transform is built on this one rotating arrow. The number to remember from this episode, 90 degrees. That is what multiplying by J really does. Next episode, the signals themselves, impulses, steps, and the two roads to decomposing anything. Subscribe so you don't miss it.